everybody. Welcome to Ms. McGuire online lectures. And today we're covering the chemical level of organization. So let's go ahead and begin. Now your body is made of elements and elements, compounds, molecules. So if you look at a distribution of elements that make up your body, you can see that most of your body by weight, 65% is made by oxygen. Then 18% is carbon, 10% is hydrogen, nitrogen is 3%. And then you have other elements, like you can see in this table, like calcium, phosphorus, potassium, sulfur, chlorine, magnesium, right? So on. So this makes, this is a small amount of microelements, but they still very essential for your body functions. And less than 1% are elements that we call trace elements, like copper, silicon, zinc, and so on. So pretty much this is the four elements, right? Oxygen, carbon, hydrogen, and nitrogen that makes about 98% of your body. Now, what are elements? Now, elements you can find in the periodic table of elements, and everybody familiar with that. Like you have hydrogen, you have carbon, you have oxygen, you have sodium, you have gold, and so on, right? Iron. So those are elements. Now, elements are made of atoms. And atoms are composed of three building blocks: protons, neutrons, and electrons. So we can use different models to represent an atom. So this is planetary model when we have what we call the nucleus of the atom in the middle, and then electrons orbiting this nucleus, like planets orbiting the sun. This is acceptable model. It's not, however, precisely correct because electrons are not orbiting. They don't have this specific orbit like the Earth, for example, has, or the moon. So we can use this, what is called electron cloud model, that is more accurate because electrons they found in a cloud around the nucleus. And proportions here are not correct because nucleus is really small compared with this distance from the nucleus to electrons. So if you imagine a football field and you put like a little, I don't know, like a pea in the middle of football field, then those electron shells, all this electron cloud, I would say, would be like a football field, and a little pea inside the in the middle of the field will be nucleus. So obviously nucleus is very small compared with this cloud of electrons that moving around the nucleus, right? But nevertheless, we do have protons, and protons we represent with this circle with plus inside because protons are positively charged, and we have neutrons, they do not have charge, and electrons, they have negative charge as shown over here. Now, if you look at the periodic table, you will see that elements, they have atomic symbol, like one letter, two letters, sometimes three letters. Then we have what we call atomic number and atomic mass. Now, atomic number show us the number of protons. So if you look at this atomic mass, oh, I'm sorry, atomic number, and it's number 6, now we know that carbon has 6 protons. So if this is a helium, helium has 2 protons. So the atomic number is 2. Now carbon would have 6 protons. And in an ideal situation, carbon would have 6 protons and 6 neutrons and 6 electrons, right? Then it would be like a neutral atom because protons are positively charged, electrons are negatively charged, right? So the carbon would have 6 protons, 6 neutrons, 6 electrons, and protons and neutrons, they have mass, and you add 6 and 6 will give you 12. All right, so that's going to be atomic mass. So atomic mass is the sum of protons and neutrons. And it's we use atomic units to as a unit of this atomic mass. So 92 elements found in nature. We do have experimentally discovered elements, and it tells us that they are not stable to exist in nature, in nature, right? So we can pretty much make those elements, and then they will decay, and some decay very quickly. Some elements that we discovered can only exist for couple seconds or even fraction of a second, and then they decay into more stable elements, right? But 92 found in nature. Now, I just told you that a carbon, let's go back, it would have 6 protons and 6 neutrons. Now, the number of protons in a particular atom is always constant, right? So carbon will always have 6 protons. However, number of neutrons can vary. And that's how we have isotopes. So isotopes are atoms when atomic number is the same, because atomic number identifies element. But the number of neutrons can be different, and it gives us different mass number. So isotopes are elements with the same number of protons, but different number of neutrons. So for example, this is hydrogen, right? Hydrogen atom has actually 1 proton and 1 electron. It does not have a neutron, right? So that's why the atomic number is 1, right? And atomic mass is 1, but it's a protein. However, it does the hydrogen exist in a form of deuterium when we have 1 proton, 1 neutron, and 1 electron, but then the atomic mass gonna be 2, right? The number is still 1, because remember, atomic number is the number of proton, and proton shown here like in the green color. So if you have this proton, 1 here, 1 here, and 1 here, oh, I'm sorry, green is this one, so I say blue, bluish. So this is proton, proton, proton. So it has positive charge. So it's 1, 1, and 1. So we know we're talking about hydrogen. Now here we don't have any neutron. So the atomic mass is 1. Here we have 1 neutron. So atomic mass is 1 plus 1, 2. And here in a tritium, we have 1 proton and 2 neutrons. So atomic mass would be 1, 2, 3, right? So here, number 3, number 2, and number 1. Now, isotopes, many isotopes are radioactive, because when we the atom became heavy with neutrons, it's not stable. So it has this tendency to lose those extra neutrons, and when they do it, they release radioactive waves, right? So, and we can pick up those radiation and make images that can show us, you know, our different organ and structures inside our body, right? So isotopes can be radioactive. Now, how electrons behave, how are they located within an atom? Now, so here you see you have hydrogen and carbon, right? For example, that's a helium. So hydrogen, we already know it's because it has a nucleus, right? And one electron. Now, electrons are arranged in electron shells, right? And we have the atom can have several electron shells. Each shell represents a specific energy level, right? So we have core electrons, so electrons that are in the inner shells, right over here inside, those are core electrons. And electrons that are located on the outer shell, they are valence electrons. Now, these valence electrons are so important that pretty much the atoms with the same number of valence electrons will have very similar chemical properties, right? So electrons of the outer shells, those valence electrons, they involved in the chemical reactions, right? Now, the maximum number of electrons in the outer shell, right, can be 8, right? So over here, 1, 2, 3, 4, 5, 6, 7, 8. And this is noble gas over here. So if atom has outer shell complete, so it has 8 valence electrons, it's in a stable energy state. It's a very stable atom, and like neon right over here, and it will not react with other atoms, right? When atoms have outer shell that is not complete, like over here, for example, we have only 4 on outer shell, but the maximum number we can have is 8. So the carbon is a reactive. It will react because it needs to fulfill its valence shell to achieve this perfect energy balance, right? Now, helium, so we can have 8 electrons on the outer shells, with the exception of the first shell that can only have 2 electrons. So helium has 2, and it's in a stable energy state, so it's not reactive. So it does not react. And neon does not react with other elements. We call them noble gases. When other elements, because they do not have outer shell that is complete, will participate in a variety of chemical reactions, right? Okay, now what is the difference? So when atoms react with each other, right? That's what we call chemical reactions. And we already know, hopefully I explain it well enough, that the subatomic particles that involved in the chemical reactions are those valence electrons. Now, when atoms react, we can form molecules, we can form compounds. Now, what is the difference between molecule and compound? So, so when we look at the matter on the Earth, right, we can have atoms, right, that made in elements. So they made of elements. So, you know, you can have just pretty much one atom that makes this element, right? When two atoms react to each other through chemical reaction, we can form molecules. Now, this is oxygen, and oxygen is a molecule because we have two atoms of oxygen make this one molecule, right? Now, molecules, usually we call molecules something that made of the same type of atoms, but it's not always true because water is a molecule, right? But it's a compound molecule. So we can have molecules made of the same element, and we can have molecules made of a different element, then we call them compounds. So what is this then similarity? Why we call oxygen O2 and HO2 both are molecules? Because these chemical bonds between two atoms are covalent bonds. Now, when we have ionic bonds between two different atoms, we call them ions, and ions are always compounds, right? They always made of two different atoms, right? So the point is molecules can be made of the same atoms, like oxygen, like hydrogen molecule, or molecules can be made of a different atoms, like over here, hydrogen and oxygen in a fixed ratio, right? But the bond between those atoms are covalent bond. Okay, next, what is solution, what is colloid, and what is suspension? Now over here, we have like a pure matter, right? Now, when we have solution, we have two different molecules, right? Or it can be molecules, or it can be ions and molecules, but we have combination of particles, right? So, for example, a solution over here, example are mineral water. So solute particles are very tiny and they do not settle out or scatter light. Then we call it solution, right? So colloid, we will have solid particles that are larger than in a solution and scatter light but do not settle out. So gelatin would be example. And suspension, when we have solid particles that are very large, they settle out and may scatter light. And examples, they give you a blood. However, I'm going to give you different example because your blood is actually all three of it. Your blood is suspension and colloid and solution, right? So, but first let's kind of make sense of this diagram. So it depends on the size of particles and how they behave, right? We can we can divide this mixture, right? So that's going to be our mixture. We can divide mixture into solution, colloid, and suspension. So we mix different atoms or molecules or compounds together, and we have this mixture. Now, obviously, your blood is a mixture of something. Now, if you look at composition of your blood is made of plasma, right? And what we call formed elements. So in other words, cells, right? Then some of them are not complete cells, but overall idea, we have plasma, that is mostly water, and red blood cells, white blood cells, platelets. Now, if you look at the plasma, you have lots of electrolytes in your plasma. Like you have sodium, right? You have chloride, those ions, right? That we call electrolytes in the biology. So now your plasma and those ions, they are in a solution state, right? Also, in the plasma, you have proteins, and proteins are organic molecules that are larger than atoms of sodium or chloride. So plasma proteins and plasma, they are in colloid state. And if you look at red blood cells, white blood cells, and platelets within that plasma, they are in suspension state because they weigh bigger particles than even plasma proteins. Right? So your blood can be example of all three mixtures. Blood is solution when we're talking about plasma and electrolytes. Blood is colloid when we talk about plasma and plasma proteins. And blood is suspension when we talk about plasma and formed elements or cells. Okay, now how those atoms form chemical bonds? So here an example of how sodium atom react with chlorine atom. Now, we already know that inside, where we have this symbol, that circle inside represent nucleus, and those blue dots represent electrons, right? So sodium has 1, 2, 3 shells, but we're really interested in this outermost shell where we will find our valence electrons. So sodium has only one valence electron. That really makes sodium very, very unstable element, and less stability, more reactivity. So it's really very reactive atom. It's so reactive that you cannot even find sodium in your pure state in nature. Because it always will react with some other atoms. Now, chlorine has 1, 2, 3, 4, 5, 6, 7 valence electrons. And it's also make chlorine very reactive. So chlorine has tendency, like every atom, they have tendency to fulfill the outer level. Now for chlorine to reach its perfect stable energy state, it needs one more electron. So just one more electron and sodium became very stable. I'm sorry, chlorine became very stable. Now sodium need to accept 7 electrons. And this is much more difficult for sodium to achieve than just lose this extra electron. Now, if sodium loses this electron, this is going to be our outer shell. And if you see, it has 8 electrons. So when sodium and chlorine, they collide, because matter is always in a state of movement. So everything moves around us. And we are moving as well, right? So when they collide, sodium pretty much steals this chlorine steals this electron from sodium, right? It makes sense. Now, when chlorine accepts extra electron, it became negatively charged, and we call it ion. And precisely, we call it an ion, so negatively charged. Now, when sodium loses 1 electron, it became sodium ion, and it has positive charge, because remember, electrons are negatively charged. So right now, sodium is neutral atoms. But when it loses electron, it has now more protons, so it became positively charged. Chlorine become chloride when it accepts electron, and it gains this negative charge. And you know, positive and negative charges, they attract, so they form a bond, chemical bond. So they stay together, and this is ionic bond. So this is how table salt is formed, sodium chloride, right? Because sodium lost electron, valent electron, chlorine gain extra electron, they became ions, and they attract to each other, forming ionic bond. Another way to form chemical bonds, and when we form chemical bonds, right, we form compounds, right, or molecules. Now, another way to form chemical bonds is to share electrons. And when two atoms share electrons, they form covalent bonds. So it can be a single covalent bond, like a hydrogen in a molecule of hydrogen. One atom has one valent electron, another atom has one valent electron, but they are in a stable chemical state and energy state when they have two on the outer shell. So they just share these two electrons. It can be double covalent bond, right? When two atoms share a pair, two pair of electrons. So this is one pair of electrons. This is two pair of electrons, or it can even be triple covalent bond when two atoms share three pairs of electrons. Now also covalent bonds can be non-polar when we have kind of equal share of electrons, but some molecules and some molecules over here, like you see water molecule, for example, they have a polar covalent bonds. Water is made of oxygen and two hydrogen molecules, and they do share electrons. So pretty much the hydrogen kind of has two electrons on the outer shell, another hydrogen has two, and oxygen has 8, right? However, those electrons are more attracted to oxygen because oxygen is more electronegative atom. So it has a bigger nucleus, right? It has some other electrons over here in outer shell. So the attraction of electrons to the oxygen is stronger, and electrons spend kind of more time around oxygen and less time around hydrogen. And then they form the polar bond. However, I don't know why it says over here minus. That should be plus and plus. And where oxygen is, we should have partially negative bond. So I think this is just not correct. So let me see if I can draw. Here, let me see if I can do it. So oxygen became partially negative. Oops. Yeah, and hydrogen part became partially positive right there. Okay. This is non-polar bond because we can see that electrons are equally shared. And we're not gonna worry about this coordinate bond. Okay, just a second. Okay, so I had to stop my recording because every time I change something, like I change the spotlight to a pen, you know, my PowerPoint stopped working. I cannot change slides anymore. This is very annoying, but nothing I can do. So this is where we stopped, right? So let's go to the next slide that give us kind of better diagram that show polar, this polar covalent bonds, right? So over here you can see again, you can see the oxygen, and atomic number for oxygen is 8. So we know it has 8 protons and 8 neutrons, and to reach this stable energy state, it needs 8 electrons on the outer shell. So that's why it's pretty much share electrons with hydrogen. But because we have lots of electrons still surrounding oxygen, way more, we have less, what did I say? Okay, we have way more electrons to surrounding oxygen nucleus, right, compare with electrons surrounding hydrogen nucleus, oxygen has partial positive, negative charge, and hydrogen is weakly positive, right? So this is weakly negative, this is weakly positive. And here how we can represent it, this is three-dimensional model, and this is structural formula. Again, that's just a representation. So you see, it's not a straight molecule. And oxygen has this partial negative, and hydrogens have partially positive pole. So polar molecules, regions of opposite electrical charge, and due to electron sharing, they are unequal in the polar molecules. Now, when we have now these polar molecules, so for example, you see 3 water molecules shown over here. Because of this partially charged pole, this is positively charged, this is negatively charged, they also form very weak chemical bonds. So there is attraction between positive part of one molecule and negative part of another molecule, right, shown over here, and those are hydrogen bonds. Now, hydrogen bonds are very weak bonds. It's interaction between partial charges. They're weak, but they're very important in biology and biochemistry. Right, so those weak bonds represented by the dotted line show us those are pretty weak, and they will be the first to be broken. If we have some, changes, like if we add temperature, for example, we change temperature, increase temperature, or it can be some enzymes. So those bonds that will break first. Okay, so what we talk about so far was matter, right? We said that your body is made of different elements, mostly you're made of oxygen. That is amazing, right? Just imagine your body is made of oxygen, right? 65% oxygen. That's incredible, right? But what else exists in our universe? We have matter and we have energy. Right, so very briefly, we will talk about energy. Now, energy can be divided into potential and kinetic. And potential is energy of position, and kinetic is energy of motion. And then we have different type of potential energy, like gravitational energy, or chemical energy, or nuclear energy, or even elastic energy. Because when you stretch this elastic, that's you change a position, right? And we already said the energy of position is potential. Kinetic, when we have some type of movement, it can be electrical, movement of electricity, radiant, movement of light, thermal, mechanical, sound, right? Now, energy, it's always exists. It cannot be created. It cannot be destroyed. So we cannot really make energy. We can make energy molecules, like your cells are capable of synthesizing a molecule that we call ATP. So we can make ATP, right? And this is used by your cells as a source of energy, but energy itself cannot be created. It cannot be destroyed. There is a constant amount of energy in the universe and always will be, as long as we know it, right? However, what we can do, we can change one type of energy. We can convert or change one type into another. We can change potential energy into kinetic energy. We can change kinetic into potential. We can change chemical energy into mechanical energy. And we can transfer energy from one spot to another spot, right? So, for example, the good example of this how we can transform one form of energy into another form of energy. Let's, for example, take your food, when you eat your food has this potential chemical energy. But because you eat your food, you use this chemical energy to move your muscles, and this will be mechanical energy. So you use this one, you convert this one into that, right? So that that's what your cells constantly pretty much doing. They're using, converting energy from one type to another type, and they move this energy from one spot to another spot. Now, chemical reactions is the interaction between valence electrons. And just very briefly, because it's not a chemistry class, we just want to know for our future chapters, we need to know what reactants are, what products are. So reactants are consumed in a chemical reaction to make products. And when you have your chemical reaction, you will have coefficients right over here. You will have your reactants. You might have some subscripts. You will have in a parentheses the physical state like gas, for example, over here, or solid or liquid. And then you have a product and a reaction arrow to show you which way this chemical reaction goes. Sometimes we will see arrows that goes both ways. That means those are reversible reactions. Now we have different type of chemical reaction. We can have synthesis, as shown over here. When we have reactant, another reactant, they combine to make product. We can have decomposition. When we start with a larger molecule or compound and we break it into smaller unit. It can be displacement, simple or double, and it can be combustion. Now, combustion or oxidation reaction, when we have one reactant and it's chemically reacts with oxygen, that's what combustion is. Combustion is in biochemistry, we call it oxidation, because this oxygen pretty much steals hydrogen ions from your from this molecule, whatever this molecule is. We will look at this on the next slides. All right, so anyway, we have a different type of chemical reaction: synthesis, decomposition, displacement, combustion. Now, all chemical reactions are either exergonic or endergonic. Exergonic, they release energy, and endergonic, they use energy to make a product, and product stores this energy that then you can use in a, then you can use the stored energy to do some cellular work, right? Now, anyway, in a chemical reaction, you either release energy when you form product, or you consume energy, you store energy within your product. Now, in biology, exergonic reaction has another name, catabolic reaction. So catabolic reaction are exergonic reaction. And endergonic reaction are anabolic reaction. So anabolic reaction are endergonic. So pretty much you either build some larger molecules and you store energy within the chemical bonds, or you break down large molecules and you release this potential energy, chemical energy that was stored inside the bonds. Right, so if you look over here, endergonic reaction, so here's our reactants. And the energy of reactants are less than the energy of products. And we have conservation of matter and we have conservation of energy. You cannot just like, why I have less energy, why I have more over here. What happened with this why those products has more energy? Because energy was absorbed. So energy was transform into chemical energy of these bonds, and now it's inside this product, right? In the biology, right, as we said, it's anabolic reaction. When you have a smaller molecules and you combine them together, forming a larger molecules, like you form big polymers, for example. Exergonic reaction, you start with reactants that have more energy than products. Now, if a product has less energy, then means energy was released, and those are catabolic reaction. And you see, you have a larger molecules, and at the end of the reaction, you have smaller building blocks, smaller polymers. So you break them apart or you synthesize them. Right now, why it's important? Because in the biology, we talk about metabolism. And metabolism is really pretty straightforward. Metabolism is all chemical reactions that take place in the organism. And by all chemical reaction, we mean catabolic reaction and anabolic reaction. Now, catabolic reaction your body uses as an energy source for energy. So you pretty much, when you have this catabolic reaction, you synthesize ATP. So you release energy. Well, you can synthesize ATP, or you can use this energy for other cellular processes. In anabolic reaction, you use ATP, and this is for growth, right? So we have energy yielding metabolism and biosynthesis metabolism, and together you have your body complete set of chemical reaction that is metabolism, right? So what would be example of anabolic reaction? So you heard probably about anabolic steroids, right? So people take steroids, anabolic steroids, to build their muscles. So anabolic reaction gonna form larger molecule. So, and this type of reaction is called synthesis. That makes sense. Synthesis means you're making something, but it's dehydration synthesis. Dehydration means you lose water. So water will be released during this reaction. So it's dehydration, release of water, synthesis, you're making a larger molecules reaction. So example, glucose, and so on, form glycogen. Now this is happen inside your muscle cells, inside your liver cells. When you have extra glucose in your bloodstream, you remove this glucose from your blood, you move this glucose inside your liver, inside your muscles, and you use glucose. You use glucose to power your muscles, you use glucose to power your brain, it's a fuel. But extra glucose, your cells will attach to one another, forming larger polymer glycogen, and you store it for future use. Also, 3 fatty acid plus glycerol will make triglycerides, that is fat, right? So you, if you have extra of these molecules, you will store it in the form of fat inside your adipose tissue. Your cells also attach amino acid, making polypeptide or proteins. This is, of course, everything happening inside your cell is very complex processes, involves many steps and many different enzymes. So it's not that simple, but the point is your cells attach amino acids forming proteins. Your cells also can attach nucleotides forming nucleic acid. So all these anabolic reactions require energy, and energy now is inside those large macromolecules. And reactions that form these molecules is called dehydration synthesis. Now, example of catabolic reaction would be pretty much the same reaction, but a reverse of them. So look, when glycerol is broken into glucose, now it's a catabolic. When triglycerides are broken into 3 fatty acids and glycerol, that's a catabolic reaction. Proteins broken into amino acid, nucleic acid into nucleotides. Right now, this will yield energy. You release energy by doing it. Now, this type of reaction is called lysis, right? Because lysis is when you break something apart, but it's hydrolysis. That means you need water to break them apart. So catabolic reactions is splitting of large molecules into smaller molecules, like digestion and energy production. So here, for example, it can be digestion if you eat all this, food, and you digest them into building units. Or another example of catabolic reaction is a very, very famous one, cellular respiration. It happens inside your cells when your cells use glucose and they use oxygen to create ATP. So glucose has lots of energy inside, right? You want to break those chemical bonds between carbon, hydrogen, and oxygen, and you want to store. When you break those bonds, you release energy and you store this energy in the form of ATP. So if you imagine that ATP is a rechargeable battery, right? So you can use it, and when you use all this energy of ATP, like you use energy in your battery, you're gonna go through cellular respiration, and this is recharging your ATP. So you're gonna form more ATPs for your future, for your use. You don't store much ATP, so this is going on a constant basis. So your cells constantly break glucose and form ATP. Now, all living cells perform cellular respiration, or at least a part of cellular respiration. So that's pretty much, you would say, it's a property of life, because we do need ATP for cellular processes. Now, but we break large molecule right into carbon dioxide and water. So that's a catabolic reaction. Now, what factors influence the rate of reaction? Properties of reactant, temperature, concentration, pressure, enzymes, and catalysts. So what enzymes do, shown on this diagram, so if you have reactant and you need to, those reactants go through, that chemical reaction, sorry for that, and you form products, even when you really release the energy over here. But for reaction to begin, you need activation energy. So you need to invest energy first, and then maybe release that energy. An amount of activation energy sometimes is like huge. So you need so much energy that your cells just cannot perform those reactions fast enough to sustain your life. That's why you have enzymes. Pretty much almost all reactions in your body are catalyzed by enzymes. And what enzymes do, they lower this activation energy. So reaction can proceed quickly with less energy required to begin the processes. Okay, I'm just taking a look how much I want to cover. Maybe I will cover up to organic molecules, and then for organic molecules, I will record another video. Okay, so here we have kind of compare organic compounds versus of inorganic compounds. And organic usually defined as compound which contains carbon and hydrogen. And of course, they contain additional elements as well. Inorganic usually defined as compounds that do not contain carbon and hydrogen. They may contain just carbon or just hydrogen. So for example, water, right? Water is an organic molecule. It has hydrogen, but no carbon. Or CO2 that has carbon, but no hydrogen, carbon dioxide, right? What other differences we have? Organic produced only by living things, so they are biotic. However, we can synthesize now in our labs, we can synthesize organic molecules. So they does not need to be now produced by living things only. And inorganic can be often formed in a non-living environment. Organic range from simple to very complex, contain strong covalent bonds. And here are some examples. Here's a sugar, protein, fat, oil, DNA. And inorganic can be made by or found in living things as well, living and non-living things. An example, we have water, sodium chloride, oxygen, right? And so on. So just the main difference between organic and inorganic compounds and molecules, that organic, they do have carbon and hydrogen. Inorganic, most of them do not have those atoms. Okay, now we already looked at your body composition when we talk about atoms, right? So remember, you are made of oxygen mostly, but when we look at the molecules, right, that make your body, then you are mostly water. And, you know, water is made of oxygen anyway and hydrogen. So about 60%, from 60 to 65, a little bit more in males and in female, weight of your body is water, right? So you can see it's 83% water in your brain. That is just absolutely amazing. Your kidneys are made 83% of water, your lungs 85% of water, your eyes 95% of water. I mean, what's going on? We're mostly water, right? 75% in your heart, even in your muscles. Your blood made, you know, the plasma is 90% of water, right? So the water is really crucial for life. You know, water is so important for life to exist that when we are looking at different planets and we're trying to find traces of life, we're looking for water. Because if we can find water, we hypothesize, we kind of can assume that life might exist on the planet. If there is no water, no life. Life is lubricant, it's a cushion, it's a heat sink, and it's component of liquid mixtures. Salts. What are the salts? Oh, well, salts are compounds, right? Mostly, so we have metal and non-metal, right, that make a salt. And it's an ionic bonding between those atoms. Like, for example, sodium chloride form crystals of salt, and we have sodium ion, chloride ion, and we have what? As we already know, ionic bond between them. Now, salts, they dissociate into ions, and in biology, we call them electrolytes. So you can see, so if we add this crystal of salt in the water, because water is a polar molecule, right? So it will be this part of the molecule that where oxygen is will be attracted to sodium ion, and this part of the water molecule where we have a partial positive charge will be attracted to chloride ions. So they will dissociate and they will conduct electrical current. Acid and bases. Now, the definition for acid is the compound, right, that donate hydrogen ions, and base, they accept hydrogen ions, right? So acids, they donate hydrogen ions, and bases, they accept hydrogen ions. So acids are able to increase concentration of hydrogen ions, and bases will decrease concentration of hydrogen and increase the concentration of OH minus ions, hydroxide ions. Acids have pH value less than 7, bases have pH value more than 7. Acids turns blue litmus paper into red, bases turn it into blue. Acids react with bases and bases react with acids, obviously, to form salt. Now, the pH of your body is critical for your survival, right? So if you look over here, this shows pH of your blood, and a normal pH of your blood is between 7.35 and 7.45. And you can see it's a very, it's a very narrow range. And if you go below, you have acidosis. And if it's below 7, it's a death of organism. And if you go above, then it's called alkalosis, and above 7.8, the cells start dying. Right, so that means it's absolutely critical to have a constant pH of your blood, of your tissue fluids, and your intracellular fluids, because this, changes in the pH can kill your cells, and as a result, kill the whole organism. So here we have like pH scale. You see the pure water is pH 7, right? And then we have urine and saliva. So we go to the acidic side and we go to the alkaline side here. And if pH getting larger or smaller over here, but look at this side. This is concentration of hydrogen ions. So more hydrogen ions we have, right, the lower is pH. So more acidic this solution is. So acidity depends on the concentration of hydrogen ions. Keep this in mind, because it will be very important in understanding of physiological processes inside cell, because when we have increased concentration of hydrogen ions, right, we became acidic, and we need to do something about it, and we need to do something very quickly, because changes in pH are very dangerous. So what can you do? If you have increased concentration of hydrogen ions, you need to get rid of them very quickly. And thankfully, you have a buffer system. So we have several buffer systems in our body. This one with the carbonic acid and bicarbonate, this is the most famous. It's pretty much explained in detail in all textbook. And this is a buffer that found in your blood, in the plasma, right? Now, what are buffers? Buffers are mixtures that capable of maintaining your pH. Buffers are a solution of weak acid and conjugate base. So like carbonic acid is a weak acid. When this acid are in a aqueous solution in the water, it will dissociate. It will be split into ions. It will be hydrogen ion, and if you take one hydrogen ion off, you have this ion called bicarbonate ion. So bicarbonate minus and hydrogen plus. So what you have in your blood, you have this whole system in your plasma. You have carbon dioxide, you obviously have water, and carbon dioxide reacts with water, forming this carbonic acid in your plasma. Inside your red blood cells, you even have an enzyme to catalyze this reaction. But you have carbonic acid in your plasma, you have bicarbonate, you have hydrogen ions. And you see those arrows, they show that this reaction can go both directions. And now what happened, I will use a pen, and then I will need to stop this recording again. because every time I use a pen, I already told you, my PowerPoint doesn't work, but I do want to show it to you. So when, for example, in your blood, you increase the concentration of hydrogen ions. So you have lots of hydrogen ions now in your plasma, right? So here. So when we have increased concentration of hydrogen ions, your plasma became acidic. So you need to get rid of them. Now what's gonna happen with them? They will be attached to bicarbonate. Oops. Right, so they attach to bicarbonate. So this reaction will shift towards carbonic acid. So you will remove this extra hydrogen by attaching these hydrogen ions to bicarbonate, forming more carbonic acid. Now, carbonic acid itself does not change your pH. What changes your pH is the free floating hydrogen ions. But if you can get rid of these hydrogen ions, make more carbonic acid, you actually became less acidic. Now, if we do not have, if we don't have enough hydrogen ions, then this reaction will shift in opposite direction. I don't know what's going on with my arrow. Then this carbonic acid will dissociate and it will release more hydrogen ions. So you became less alkaline. You increase your acidity if you need to, right? So the point is, because of this buffer system, when pH of your blood plasma changes, either you have oh my goodness, I cannot handle it. That's so funny how I draw this stuff. So if you have high concentration of hydrogen ions, right, then the reaction shifts towards carbonic acid. If you don't have enough hydrogen ions, then reaction will shift towards bicarbonate and hydrogen ions. That makes sense? Hopefully. And of course, now I cannot move to another slide, so I need to stop my recording for a second. Okay, so anyway, I hope you guys have some understanding how buffer system works. Right, so so I just gonna quickly repeat it, just spend another 1 minute to do it. So this buffer system is called carbonic acid bicarbonate buffer system. It's found in your blood plasma. That means you have a weak acid, that is carbonic acid, and you have its carbonic acid conjugate base, that is bicarbonate, because carbonic acid will split into bicarbonate and hydrogen ions, but not all the acid will split. So you will end up having all of this. You have carbonic acid, you have bicarbonate and hydrogen ions in your plasma. And that's so perfect, because when the amount of hydrogen ions increases, you can attach these hydrogen ions to bicarbonate, and you make more carbonic acid that removes hydrogen from solution, making you less acidic. If you don't have enough hydrogen ions, then more carbonic acid will dissociate into bicarbonate and hydrogen acid. If more carbonic acid dissociate, you increase concentration of hydrogen ions, and you need it if your pH goes too high, right? If you don't have enough acidity, because remember, you need to be right there in a normal pH, right? Okay, so this is where I will stop, because the next part of this chapter is about organic molecules, and I'm gonna record my second video because it's really getting very long. So I'm sorry for this lecture to being that long, but I just trying to trying to explain every single slide instead of just reading from it. So thank you for watching, and I hope it was helpful.